fonts, both here. I did some of my graduate work here, and also on campus, including my office, which has remained exactly the same. So today, as was alluded to, I'll tell you a little bit about some of the research I do, and sort of a smorgasbord of different physics that I happen to have picked up during my career. And because you're a captive audience, I'm going to start things off as everybody loves to start with, but a pop quiz for everybody. I like to ask the audience to take a guess as to what this picture is. Do I hear $50? A little louder. Someone brave enough to just shout it out. The back of an eyeball. But now I will never look at that picture ever again in the same way. Someone else? The sun. Okay, great. We got halfway there. The next part of the quiz is, where was this taken? We got a top of the mountain. Underground. Maybe someone read the byline. All right. So, excellent. Give that. When I do this lecture, I have usually candy and I throw it at people, but I think that would go over poorly. So, as was correctly guessed, this is a picture of the sun. It is taken with neutrinos. It is taken with a camera that's 12 meters across. It is located 4 miles underground. And it took a year to take it. Now, I like to break this down because this sort of tells us a lot about what the hell neutrinos are. So there's a lot we can learn about this picture. The first is what this is really a picture of. This is not a picture of light that we expect from the sun. This is a picture of neutrinos that are coming from the sun. Now, some of you may know what neutrinos are. Some of you may not. So particle physicists have a periodic table. Just like you learned in chemistry, you got all the elements putting together. Particle physicists also have a periodic table. And our table's got fewer things in it, thank God. And that's why I became a physicist. I don't have a very good memory. I can't memorize the whole periodic table. But this I can handle. So particle physicists divide the world into either your matter, and matter are the colors you see on top. So the one you probably are familiar with is the electron, right? It's the thing that goes around your hydrogen atom. You probably learned that in chemistry. The electron has a couple of siblings. The one that's a little bit heavier, but otherwise looks exactly like an electron, is called the muon. And its heavier brother is called the tau. So electron, muon, and taus, and those happen to be matter. The muon is unstable and decays. The tau is unstable and decays. The electron, it's the lightest thing, it doesn't decay. The electrons have sort of cousins. The cousins are neutrinos. You'll see them below. There are 3 of them. An electron neutrino, a muon neutrino, and a tau neutrino. So that's one side. You say, wait a minute, I also know there are protons out there. Protons are indeed part of this, but protons can be broken up. And you may have heard of quarks, and the quarks are sitting on the top part of that table. So you got up and down, strange and charm, top and bottom. It was the 60s. People were very creative. So those are the particles. When you think of, when you say matter to a particle physicist, that's what matter is those types of particles. Now, you may have also heard of forces. Forces, well, those are also particles. So a particle physicist, everything's a particle. You know, if you have a hammer, everything's a nail. So same here. When we have 4 forces that we know about, we have the electromagnetic force. That's your ordinary how particles with charge talk to each other. Then you get sort of more exotic. They're the weak force. The weak force is responsible for radioactive decays. And then you have the strong force. And the strong force is what binds those quarks together. So those are the forces. And we also have, you may say, what happened to gravity? Particle physicists don't understand gravity, so we don't even put it on the table. At the very bottom, you have the Higgs. The Higgs is also a particle, but this is our best way to understand how particles get massive. The Higgs mechanism was a way in which we figured out why particles have mass at all. And that could be a whole new lecture, but I'm not going to talk about that. So that's our periodic table. And usually, when we look at the sun, we're seeing light. And light is photons, and that's the electromagnetic spectrum. But the sun also makes a whole bunch of particles, some of which are neutrinos. And those are what's coming from the sun. All right. So neutrinos are really special in this picture. For one, unlike the electron, which has a charge, and unlike the proton and the quarks, which also have charge, neutrinos do not have charge. And to a particle physicist, when you don't have charge, you can't talk to other charged things. So neutrinos don't like to talk using photons. They just don't. They're also unlike quarks. Quarks talk to each other all the time. And we assign this thing as color. It's the word for it, but you can think of it as like a charge. And that's how quarks talk to each other and communicate and exchange energy. But neutrinos are not quarks. So they don't see the strong force. They're completely blind to it. In fact, the only way neutrinos interact in the world at all is through the weak force. Now, you may now gather, I keep calling it the weak force. The weak force is weak. And that means the neutrinos don't really like to talk to anything. And the neutrinos that are produced in the center of the sun just zip right through. They're like, I don't have time for you. I am just zipping by, and they stream out from the center of the sun all the way to the universe. Some of them hit us. Some of them hit that camera that I talked about. All right, so now you're experts in the periodic table for particle physicists. By the way, we refer to this as the standard model. This was after the 60s, so we were less creative. All right, the second is the sun. All right, so this is a picture of the sun. You may say, well, where do neutrinos come from? Where can I find neutrinos? And it turns out that the universe is absolutely filled with neutrinos. So, at the center of nuclear reactors, you make neutrinos. Inside the stellar core, including our sun, you produce neutrinos. There are accelerators, some of which in this complex, old ones that are dismantled, that produce neutrinos and still do at other experiments. The center of the Earth makes neutrinos. Distant galaxies produce neutrinos. And in fact, at the very beginning of the universe, there was a lot of light and there were a lot of neutrinos. So the neutrino scape is everywhere. They're really all around us. Okay, but the sun, it's really close. It produces a lot of neutrinos, so it's very bright as a neutrino source. Now, the other thing about this picture is that it was taken with this camera, I say camera in quotes, 12 meters across. Neutrino physicists like to build very big things. So I love this picture. This is a picture of Ray Davis. He was actually a chemist who conjured an experiment called the homestake experiment. As you'll hear often, a lot of these experiments are underground. This was one of the first big ones that was ever built. It was built in the homestake gold mine in the 1960s. That's him standing in this giant tank that eventually will be filled with, I forget if it's 200 tons of chlorine to look for neutrinos from the sun. But I just love this picture of him sort of staring out at this giant tank. And experiments of this sort tend to be very large. Now, as I have already hinted, A lot of these experiments are also underground. Now you may ask, why would you want to go underground for something like this? I'm going to pose that as a question. Why would crazy physicists like us, aside from being away from people because we're not very social, want to go underground for these kinds of experiments? You over there.
Because if you're just looking at neutrinos, you don't want other stuff floating around.
That is perfectly correct. Yes, you want to get rid of everything else because neutrinos don't like to interact very much. Other stuff really loves to interact with these experiments. So you want to go to someplace quiet so you can just listen to neutrinos. And that's indeed why we do that. And that's because our Earth is constantly bombarded by cosmic rays. Cosmic rays actually tend to be a lot of those other particles that I told you about, those muons and other quarks. They get produced in the very upper atmosphere. These are giant hydrogen atoms that hit the upper atmosphere. They collide. They release their energy and produce a shower. You don't see it typically, but those showers stream down, and on a typical, small amount of area, you have hundreds of muons and other particles going through it at any given time. And the only way to get out of the way is to drop down deeper and deeper. So as you go down in depth, it gets lower and lower. This plot shows the different giant underground laboratories that have been built over the past 60 years to get away from that muon flux. The deepest one was a gold mine in East Africa. The second one was in South Africa, and the other one in India. The one that I'll talk about is called Snow Lab, that was built in Canada. But you have to go very deep underground to get rid of all those cosmic rays. And actually, it's not just cosmic rays that you have to worry about if you're a neutrino physicist. Because remember, there's radioactivity everywhere. And I love this poem. It's by T.S. Eliot. And in it, he talks about there is shadow under this red rock. Come in under the shadow of this red rock, and I will show you something different from either your shadow at the morning striding behind you or the shadow at the evening rising to meet you. I will show you fear in a handful of dust. To a neutrino physicist, this is terror. That's because the dirt that is carried from your shoe has trace amounts of uranium and thorium. And then you're going to go home, you're going to like, oh my God, there's uranium and thorium in my shoes. I got to take a shower. Don't let me talk about bananas. Bananas are like hugely radioactive. To a neutrino physicist. I can see the viral videos already. It's like, don't eat the bananas. But uranium and thorium are these unstable particles that have a really long, it takes them a long time to decay. So they're hard to get rid of, and you only need a tiny bit in order to ruin an experiment. So trace amounts of just plain old dirt is enough to ruin these experiments in terms of being able to see neutrinos. Nevertheless, we still try to build these giant experiments to get away from all these cosmic rays, and we try to build them in these ultra clean environments underground in order to minimize the amount of dirt that can seep into our sensitive experiments. I was a postdoc on one of these experiments that I'm showing, which is the Sudbury Neutrino Observatory. And in order to go to work, I would have to put on my suit, and it was an active mine in Sudbury, Canada. And you get in with the miners. This is an active mine, so there are a bunch of miners who are there for their job. But also underground in this place is a underground laboratory for neutrinos. So you get in the cage, and you scrunch up with everybody else, and you see how tall I am, and you can imagine tall miners all around me, and I'm just kind of like, okay. And the elevator zips down. It takes about 15 minutes to get to your level. And then the doors open, they push the physicists out, and then they close and they keep going down because that's where the nickel is and other precious material. And then we walk about a mile, and at the end there is a door, and you take off your clothes and you should take a shower because you are dragging all that dirt with you, which has uranium and thorium. And on the other side, there are clothes waiting for you, and you put on the bunny suit, and you're in the cleanest environment in northern Canada. So I can say that I have taken a shower 4 miles underground. It was fun. And as you can imagine, even with all this, it still takes a really long time to collect enough data to make this picture. So this one, I think actually was even more than a year, but I like to kind of quote that this is the time scale it takes to get that exposure so that we can image the sun in this way. Neutrino experiments just take a really long time. And just as an illustration, when neutrinos were first proposed, it was done by Wolfgang Pauli in 1930. It was through a telegram to a scientific conference where there is this big debate at the time talking about the issue about radioactive decay. They were worried that this sort of tenement of nuclear physics, which is energy is conserved, was no longer true. And people were trying to figure out what it was. A famous physicist named Hans Bethe conjectured that maybe energy is not conserved at the really small particle level. But Pauli sends a telegram and he says, I'm going to do the craziest thing. I'm going to propose that there is actually a particle that comes out of these decays that you can't see. And it just zips away. And I'm going to call it, actually he called it at the time the neutron. But then when they found the neutron, he said, no, that's too heavy. It's smaller. It's called the neutrino. So that's, because Italians put ino to make things smaller. So that's what Pauli suggested. Incidentally, that very telegram is it's kind of interesting because then he says why he's not coming to this famous conference, and it's because he has a date to the ball. So the man had the priorities. Later on, an Italian physicist named Enrico Fermi kind of wrote the theory that it first incorporated the idea of neutrinos and the weak force. But it then took 26 years in order for it to first be experimentally discovered. That's by an experiment called Poltergeist by Ryan and Cohen back in 1956. And when they announced their discovery, they sent a telegram to Wolfgang Pauli. All right. So after all this, you said, why the hell would you do all this to yourself? Why study neutrinos? And it actually turns out that neutrinos are the first real crack at that standard model that I showed you that's supposed to explain everything in terms of particles and forces. And one of the reasons is that the standard model would really like the neutrino to have no mass. But it turns out that actually neutrinos do have mass, and that has spawned a huge amount of research in nuclear and particle physicists. We broke that standard model that people wrote down that we thought could explain everything. Now, I want to give a little bit of context as to how do we find out more about these neutrinos and what's this mystery about neutrino mass. And for this, I have to sort of put you in the minds of a neutrino physicist back in the 1960s. So remember that big experiment I mentioned, the one of Ray Davis with the giant tank that he was staring at. Well, he did that so he could count neutrinos from the sun, because there was a prediction that said, this is the sun, it's burning fuel, it's converting hydrogen eventually to helium, and that process produces neutrinos. I'm going to count how many neutrinos are coming from the sun and be able to look at the very core of the sun. And he did that. And it took him 26 years for his experiment to gather that data. Very patient man. And at the end of the day, he started counting how many neutrinos he got. And he noticed that he kept coming up short by about a factor of 3. And you can imagine, physicists are very critical of each other. So he says, you probably did your experiment wrong. And other piece says, oh, you probably did the calculations wrong. So it's easy to be off by a factor of 3. But other experiments started to come online, and they kept on measuring a factor of 3. And theorists kept on going to their calculations, and they made other predictions that the sun sort of checked out. So something was really amiss. So one possible solution came from the idea that, remember, I had 3 neutrinos out there. Well, the sun is only able to make one kind of neutrino, the first one, called the electron neutrino. There's only so much energy in the sun to make them. And the experiments on Earth could only see one type of neutrino. They could only see electron neutrinos. So some people said, well, what if those neutrinos are changing to the other types? So you start out with red and you end up with green. You still have the same number of particles or balls, but the color is different. If you can only see green, you'll miss the other colors. So the idea was maybe these neutrinos are changing their flavor. This process is known as oscillations. And it was conjectured, not many people believed it, because oscillations can only happen if neutrinos have mass differences. And to illustrate that and remember, the standard model did not want neutrinos to have mass. They were massless. So this kind of broke a couple of things. Now, you may be starting to scratch your head and like, oh, the parking lot's full, I can't get out. How do I wrap my mind around this idea of neutrinos changing flavors? And I'll give an analogy. For this exercise, I took a tuning fork, and 2 of them, and I just hit them one after the other. For those who have perfect pitch, do you know what note that is? Does anybody know what note that is? A, G. I actually have no idea. I don't have perfect pitch. And I did this like 10 years ago. I don't remember what the note was. I think it's A. That seems to be the most common answer. But even if are any of you musically inclined? Just kind of show by raise of hands if you play an instrument. Okay. So for you, I don't mean to pick you out, but was it hard for you to say, oh, that's exactly the note?
Well, the sounds were so different. One was very muffled.
Oh, that's just because I have bad recording. But typically, it's pretty hard to kind of guess exactly what that note is. I had a friend of mine who did have perfect pitch. He could tell you what note the microwave tune was just by listening to it. I don't have that ability, and it's a really hard ability. You have to be really trained in order to see it. It takes a lot of calibration and knowing exactly what that is. Now, and presumably the 2 forks are pretty similar. And the graph that you see is how the sound appears in frequency space. Now I'm going to put a piece of gum on one of those tuning forks and do the same exercise. It's oscillating, and they're not the same note. Yeah, you change the tuning fork by putting a piece of gum on it, and all of a sudden, you have a slight difference, and everybody could hear that, right? Everybody picked up like, oh, there's that wah, wah, wah sound. That means that these two notes are not the same, and you're hearing a slightly different note. Keep that analogy, because that's exactly how neutrinos oscillate from one type to another. But you need that difference. Now, for neutrinos, that difference is mass, but the effect is the same. You get this vibrating pattern that's a lot easier to measure than telling you what the note is. The other analogy I like to use is you go to, well, I'll save that analogy for later. Back in 1985, a brilliant physicist by the name of Herb Chen wrote a paper where he said, look, I can measure neutrinos from the sun, and I can devise a way in where I can look at electron neutrinos and any flavor with the same experiment. The key was to use heavy water. So instead of regular water, it has an additional neutron in there. So that's why it's called heavy water. And he wanted to build a giant tank underground in order to look for neutrinos from the sun that picked up between one type and all types coming from the sun. This is where that experiment lived. It's in the Sudbury Neutrino Observatory in Ontario, Canada. That giant shaft there is the pulley that brings the elevator down to the lowest level. I have taken that elevator several times. This is a cartoon of what that looks like. So carved in the rock, you go from above, and there is this giant structure. Above you is 2 kilometers of rock, so that's about 4 miles. The inside is a kiloton of heavy water lent from the Canadian power companies, that's how they build their nuclear reactors, on loan for $1 Canadian, 90 cents US. But it was loaned, so we had to give it back. And what better way to store really precious heavy water than a bunch of physicists who really like to have it for a small amount of time? When neutrinos interact with the heavy water, they produce light. Oh, very occasionally, that whole thing gives you 10 events per day. But they produce these light cones, and all around you see the little dots. Each dot is representative of a phototube, which is a light sensor. It's about the size of my head. This is actually a picture of it, photo eye lens from the top. You can see here, these little dots are about this size, so you can imagine how big it is. And after all that, it was built. But unfortunately, Herb Chen died before he saw the experiment see first data. But it actually took data and did see this difference. It counted the electron neutrinos, measured a third, and then it counted all of them, and it was perfectly in agreement with the sun. And that can happen if the neutrinos that are coming from the sun are changing to a different type. And of course, scientists are like, well, I don't know, so they built a whole bunch of other experiments. So this is some pictures of these kinds of experiments. There's the Ray Davis Jr. at Homestake. That was the original one that looked for neutrinos from the sun. Then the Sudbury Neutrino Observatory up there. Another one in Japan called Super Kamiokande, which was even bigger, was built. Then people started shooting neutrinos from beamlines. That's the Minos experiment on the top. And people built neutrino detectors near nuclear reactors and also looked for this changing. And all of them agreed with each other. When you do that, you get the Nobel Prize. So Art McDonald won the Nobel Prize along with Tayaki Kajati from Super Kamiokande. I apologize for mispronouncing his name. And they established that the prediction from the Standard Model that neutrinos were massless was no longer the case. And that came out of underground science. Now we can ask, okay, well, why don't you tell me more about this neutrino mass? And it turns out that we still don't really understand how neutrinos get mass. They're much, much lighter than any other particle that we know of, by factors of 1 million. They have mass, but it's really low. We don't even quite sure if the same mechanism that we understand masses for other particles applies to neutrinos. So that the jury on how neutrinos have mass is still out there. And you may say, okay, after all that, can you at least tell me how much they weigh? And actually, I can't. And the reason for that is because right now all we have done, remember the tuning fork, you were measuring differences. With differences, it's like you go to a car dealership, so I'm going to give you a great deal on the car. I'm going to get $5,000 off of your vehicle just because I like you. And you're like, that's great. I'm glad you like me. I'm glad I'm getting this deal. How much is the car? Did I tell you about the $5,000 that I'm taking off of the car? Would you just buy the car offhand? I would say you want to know the price of the car. All I know is how much difference I have, but I have no idea where I start out. Oscillations only tell you that there is a difference. It does not tell you what note they're playing. So you need a bunch of other experiments. And I can give a completely separate talk on that, because that's actually my research, what I do now. But we're trying to figure out how to measure neutrino masses. I kind of skipped a little fast on that. This is not how we build a neutrino mass detector. I wish it was that simple. ChatGPT, this is, I said, how do you measure the neutrino mass? And this is what it responded. And I'm like, okay, that's great. You can look out to the cosmos. And remember, there's a whole bunch of neutrinos out there. You can use cosmology to tell you what neutrinos' masses are. They're trying that. You can look for really, really rare decays that are sensitive to neutrino mass. And there's a whole science trying to do that. My personal way is to actually go back to the basics and look at basically the idea of E equals mc squared. Or for a neutrino physicist, whether energy and momentum are the same thing. That's usually the key for figuring out how much a particle weighs. And it turns out, you may recall that I talked about Enrico Fermi. Enrico Fermi, back in 1934, told us how to measure neutrino masses. It was actually, to be technical, Francis Perrin in 1933 suggested that a way to look at neutrino masses is to measure the decay products from a radioactive explosion. Enrico Fermi made the same conclusion in a paper in 1934, where he writes, arriviamo così a concludere che la massa del neutrino è uguale a zero o ogni caso piccolo in confronto della massa dell'elettrone. Thank you. I can't do the French. But the Italian, I'm always happy to say, the translation of that is, we conclude, based on this paper, that the mass of the neutrino is equal to 0, or in any case, small enough compared to the mass of the electron. This was the first quote-unquote measurement of the neutrino mass. They said, it's probably lighter than the electron. And then he drew this picture in his paper. I loved this paper, first of all, because it was rejected by Nature, but it completely revolutionized nuclear and particle physics. So, if you're a writer and you send a manuscript out and they reject it, don't worry, you're a genius. They just don't recognize your genius. In this picture, he draws this curve, and he's not talking about coffee. So there's grande. That's big mass. So grande is large. Piccolo means little. And the spectrum will look slightly different. Or zero, and the spectrum will look like that. Grande is already ruled out. Piccolo is pretty well ruled out, and all that's left is close to zero. By the way, I also love this picture. This is the ragazzi di Panispero. So there's a bunch of very famous nuclear physicists in Rome in the 1930s where he trained. And it's a very Italian photo. Like, I have a similar one of my dad. He's not a physicist, but, you know, standing around with friends. They're just not smoking, which is usually the picture. So the idea is you want to take a lot of radioactive material. And my favorite is tritium, because it's the easiest to study. And when it decays, it produces particles. One of them is the electron. And if you measure the electron's energy as precisely as you can, and look for a tiny, tiny, tiny deviation in the spectrum, that spectrum tells you about the neutrino mass. And this is the more technical part of the talk, so I'm going to skip over that, but I'm very happy to answer questions. This is my life, is making that plot. However, we get to build very large machines again. So this is my other experiment. This is the Katrin experiment. It's located in Germany. And it's, I'm trying to turn on, here we go. This tank is used to help select the energy of the electrons that come from that decay. And for the engineers in the audience, if you're interested in the clearance on both sides of those buildings, it's 2 centimeters. What's also interesting about this thing is it started over here. This is where the tank was built. And there was no road that would connect you to where it was supposed to go that didn't take out a bridge. So it went down the Danube around here. It actually stopped at my hometown in Catania. There, I'm glad they didn't steal it. And then it went back, and this picture is taken right as it goes into its home. And now it's taking data and trying to set and actually measure the neutrino mass value very precisely. When they do, I'll ask Mike to invite me in, and I'll tell you about that. You don't actually have, oh yeah, this is a picture of it being lowered into the lab where it eventually lives. You actually don't have to build these giant detectors. You can go really, really tiny. So there's a group in Italy and a group in Germany that try to measure this radioactivity with really tiny, ultra-sensitive detectors. So this is about a little bit less than my size. But that's actually not the whole experiment. If you zoom in there, you see a chip, something that looks like a chip. And if you zoom in on the chip, there's a little gold pad. And that little gold pad is a tiny bit of radioactivity, but they measure it so precisely that can actually determine that spectrum and determine the neutrino mass from that too. So that's also running. So you can go big or you can go small. So we'll continue, and I'll give you an update if we actually measure the neutrino mass with a positive value. So that was all spurred by this experiment or series of experiments that happened underground. So what other discoveries might come from the underground? Well, people remember, you're away from a lot of cosmic rays, so it's a great place to look for things that are very, very hard to see. Dark matter is one of them. So the universe is surrounded by dark matter. Nobody knows what it is. People think that it's a particle, and if it's a particle, eventually it will interact with your machine. And so they build these super quiet, large tanks in order to look for dark matter. You can probe whether the neutrino matter is the same as antimatter. So building other experiments, again, very quiet places underground. You You can even answer the question of whether there is something instead of nothing. There's a huge program that Columbia is very involved in called Dune, which is trying to answer this question. And again, they build these giant experiments underground to get away from all those cosmic rays. Now, so lots of possible discoveries. Sorry, it's going a little fast. Oh, I know why. Because it's, sorry about that. I can't see anything without my glasses. There we go. So, yeah, so, you know, this is keeping us entertained as scientists. There are lots of discoveries. It's, you know, lots, you know, exciting, fun. But, you know, part of you is probably saying, well, can you do something useful with this? And I'll make a pitch for it, which is still science. So one of the things that you may have heard, you're going to hear about in the next series talk in December, is quantum. And by that I mean people right now are on the brink of trying to build the first actually useful quantum computer. This was actually an idea that probably was coined by a keynote address by Richard Feynman to MIT back in 1981. And he conjectured that the best way to understand how nature works, and nature for us is understanding quantum mechanics, that you want to try to simulate it. And the best way to simulate quantum mechanics is with a quantum computer. You use the atoms as the way in which you probe the nature of quantum physics. And it actually turns out that for some problems, quantum computing is really, really useful, and particularly in chemistry, in physics, in mathematics. And so there's not just participation from scientists, but there is also participation from industry partners as well, because they realize that if we crack the code, then we'll be able to actually harness these machines to make very difficult calculations much easier. And you can ask why, and honestly, nobody really understands quantum mechanics, but it's taking advantage of the fact that you're dealing with particles, so quanta. Two, that particles can superimpose on each other. That's the magic of quantum physics at the microscopic level. And that particles can be entangled with each other, where one thing happens to one and it affects the other one, magically almost. So these parts of quantum mechanics actually help in terms of making certain calculations much, much easier. So in terms of usefulness, people think about quantum physics for cryptography, for simulations, for chemistry, for optimizing certain problems. And there is a genuine push in trying to build the first quantum computer that's useful. Now, it'll probably take another 20 years. But we're closer now than we were certainly when Feynman said his statement. Now, the building block for something like this is similar to what devices on your computer are. At the end of the day, you have to have a bit, something that does a calculation. And people have devised all kinds of ways to do it. The two leading ones are superconducting qubits. They look a lot like the circuits on your computer and phone. Some people take single ions, single atoms, and manipulate them. That's also been quite successful. And right now, it's sort of like a battle between who's going to win those two cases. By the way, the picture in the middle is a quantum computer built by D-Wave, a company. It's not a scientist. I mean, it is a scientist, but I mean it's an industry product. It doesn't do much, but it is available. I hope nobody from D-Wave is watching this video. Sorry. Now, for quantum bits, one of the magic is that you want the different bits to talk to each other coherently. That's how quantum computer works. But as you can imagine, sometimes your bits, well, they make mistakes. So you have a computer is quietly acting coherently with the other qubits, and very occasionally one of them screws up. And that's okay. That happens with your computer also. Occasionally your computer will, accidentally was supposed to have a 0, it got a 1, but it has ways to correct for itself. That's also true for quantum bits. They want to, you can try to correct for them. And the basic idea is, look, it's okay if you make a mistake. As long as not everybody makes the same mistake at the same time, I can fix you and correct myself. This in the industry is known as quantum error correction. It takes advantage of the fact that quantum bits are tangled with each other. And says if occasionally one of them screws up, I can still recover from that. The problem is when all of them start behaving badly. So if all of them start to light up at the same time, this quantum error correction doesn't work. And as you might imagine, a cosmic ray that hits one of these chips will do exactly this. So, this is the only other plot I have in my talk. Recently, Google showed this quantum error correction idea and was able to show, look, as I add more and more qubits, it gets better and better. And ideally, the dots would follow that line. And you notice that toward the bottom, they start drifting off. That spot is a cosmic ray starting to poke at your machine and screw things up. And that's on a machine that's, of course, on the surface. So I like to tease my quantum computing friends and say, you are bound for this. You're about to go underground to get away from cosmic rays. And we actually don't know the answer to that. We don't know if cosmic rays are going to definitely kill trying to do quantum computers on the surface. All we have been able to show so far is you have to think about it in order to correct for it. Luckily, people are very, very clever because a lot of the techniques that we have learned for neutrino physicists to look for these really rare events carry very nicely to this realm as well. So, like all these experiments, you can put a bunch of shielding in front and get rid of all that nasty uranium and thorium. You can be very careful about the materials that go into your machine to make sure that there's no radioactivity. And, eventually, maybe you have to go underground. Hopefully not, because they get really squeamish when you have to go underground to do these quantum computations. Okay. Well, with that, I'm gonna stop here, and hopefully I gave you a taste of the exciting things that can happen many miles underground. They have led to many exciting discoveries over the past few decades, and very likely your next big discovery is likely to come from below the Earth. And with that, I always thank you for your attention.